Okay, last problem in chapter 4. Um, so this is a pretty involved problem, but it's one that's similar to a WebAssign problem, I believe. So as I go through this, I'll kind of talk about the nature of the WebAssign problem and give you a couple hints. So I've got two blocks connected by a string over a pulley. Again, pulleys are massless and frictionless. One of the masses is resting on an inclined plane that's angled at 30 degrees. So the block that's on the incline, the hanging block, is 16 kilograms, and then the one resting on the plane is 8 kilograms. We've got a coefficient of friction between the blocks and the surface. So the blocks are made out of the same material. The surface is the same everywhere. So we have mu, we have the coefficient of friction between both blocks and the surface. So we're looking for the acceleration of the blocks and the tension in the string. So this is very similar to a Newton's second law problem we did earlier before we introduced friction. So the blocks are connected by a string. So two things we know. They're going to have the tension is going to be the same everywhere in the string. Right? It's one cable, same tension. Also, the two blocks are connected, so they're going to have the same acceleration. All right. So here's my picture. Again, we're picking a certain direction to be positive. A couple problems ago, we had one that was hanging and then one that was resting on a surface, and we picked the one that was hanging. If it was descending, if it was going down, we picked that direction to be positive for that object, so it would match the resting block. We're going to do the same thing here. So when an object, when M1 or M2 are moving in this direction, we're going to say that's the positive direction. So when M1's moving to the right and M2 is sliding down the incline, we're going to say that's the positive direction. So my free body diagram for M1 looks pretty normal, right? We've got tension in the positive x, the force due to friction in the negative x, the normal in the positive y, and gravity in the negative y. Now my question here is, I'm making a prediction again. When I draw my free body diagram, M2 is twice the mass of M1. So I'm going to make a prediction right now, and I'm going to say that this system is going to move in the positive direction. So I'm going to draw my friction force vector in the negative x direction. To oppose the motion, I predict the system's going to go in. Okay, and the acceleration value I get for Newton's second law should verify that I'm correct in my assumption. Free body diagram for M2 looks like this. Remember, I've studied my inclined plane. I'm splitting my gravity vector, which is pointing down. I'm splitting that into the y component and the x component. Right? The x component is mg sine theta. Y component is mg cosine theta. Tension is pulling in the negative direction on M2. M2 is on an incline, so there's a normal force, and we've got the y component of gravity, mg cosine theta, and then we've got friction force on block 2 opposing its motion. So here are my two free body diagrams for these objects. Again, t is going to be positive, m2g sine theta is going to be positive. That's the positive direction for this system. So Newton's second law for M1, we've got tension minus friction is M1a. Right, we're being asked for the acceleration, so I'm assuming the system's going to accelerate. In the y direction, normal minus mg equals 0. So we're dealing with a friction problem. We're going to need to know what the normal force is, because friction is mu times the normal. Normal is m1g. Okay. For M2, in the x direction, we've got m2g sine theta down the incline, tension, and the friction force up the incline. So mg sine theta is positive, tension and friction are negative. M2 is also going to have an acceleration, so I'm going to solve for that. Both of these are the same, right? They're connected by a string, so they're going to have the same acceleration. In the y direction, we have to watch for this because we're on an incline. Normal in the positive y, m2g cosine theta in the negative y. So the normal force on block 2 is m2g cosine theta. Okay. So I've got a system here, right? Newton's second law in the x direction for both objects. Friction is mu times the normal. I know the coefficient of friction, it's 0.23. I know the normal force for each block, so I can calculate the friction force for each block, and I could solve this system. Right? It's two equations, two variables. I can solve it. But again, I want to see if I can avoid that by defining my system as both of the blocks. Alright? So take your picture, draw your system bubble, right? Or draw a circle around both your objects. Right? So now we've got a tension force that's inside my system. Alright, so it's my M1, M2 system, the tension is inside, that's an internal force, it's not causing the system to accelerate. But when you draw your circle around M1 and M2, we've got external forces. We've got the normal forces, yes, we've got the y components of our gravity, right? We've got this force right here, but they are not causing the system to accelerate. Right, these are y direction forces, right, or these are perpendicular to the system's motion, so they're not contributing to the acceleration of the system. What is contributing to the acceleration of the system? m2g sine theta, the friction force on m1, and the friction force on m2. So both these friction forces are outside of the system because they're due to the surface, and the surface is outside of our two block system. So m2g sine theta is a positive force. Friction on 1 and friction on 2 are negative forces. Okay, so here's my quote-unquote free body diagram for my system. Right, total mass is m1 plus m2. I've got m2g sine theta in the positive direction and the two friction forces in the negative direction. So Newton's second law for the system, I've got one equation, which hopefully everything that's in the equation I have, with the exception for the acceleration. I can solve this for A. So solve this for A, divide both sides by the total mass. Remember, total mass is m1 plus m2, which I know. So the acceleration is m2g sine theta minus mu times the normal force on m1 minus mu times the normal force on m2. Those are my frictional forces, all divided by the total mass of the system. So I've got my two expressions for normal forces here, m1g, m2g cosine theta. I'm substituting these two expressions in for the two normal forces. Okay, so I've got this in the numerator, right? Mu times the normal on block 1, mu times the normal on block 2, divided by the total mass. Right? Plug everything in, save yourself a little bit of room here because we've got a lot of values to plug in. But if my calculations are correct, I've got an acceleration which is positive 1.2 meters per second squared. So now I can take, now that I have the acceleration, I can take either one of these, and I can take either one of these to solve for the tension. Okay, it looks like this one probably would be easier, right? Looks like this one would be a little bit nicer to handle. So I'm going to add the friction force to both sides, get the tension by itself. So T is m1a plus the friction force on m1. Sorry, I forgot my subscript there. That should be a 1 right there. Tension equals m1a plus the frictional force on m1. I know what the frictional force is on m1. It's mu m1g. So I substitute my mass in, right? This is m1. Both of these masses are m1. 8 kilograms. I know the acceleration from the first part. I know mu, I know g, and I get the tension force. Okay, the magnitude of the tension is 27.6 newtons. Now, a WebAssign issue is it's very similar, right? So my free body diagrams would be very similar. A couple things about the WebAssign problem. I do believe M1 and M2 are made out of different materials. So what happens is the coefficient of friction between the block and the surface is different for M1 and M2. So down here where I just use mu, right, friction force, mu times the normal, mu times the normal. These two coefficients of friction are going to be different for each block, so watch out for that. Also, it starts out as a static friction problem. It starts out as a static friction problem because the system is released from rest. So I believe you're given different coefficients for static friction than you are kinetic friction. And you're supposed to make a prediction. You're supposed to predict if the system is actually going to move. Right? I think you determine if the system is going to accelerate from rest. Okay. So basically, you're looking to see if this component of gravity is large enough to overcome these two friction forces. So we can still set it up the same way. But we have to use different coefficients of friction to see if static friction is overcome by that gravity component here. And then I'm not sure if it actually does or not. So figure that out, get the acceleration. If your acceleration is positive, that means that the system is going to accelerate. And then I think you're asked for something else after that, and you have to use the coefficient of kinetic friction for the two blocks. So you got to go back and forth between the coefficients, and they're different because they're different materials. So a little bit of extra work there on the WebAssign problem, but it's a similar concept. Hope that helps. This is the end of chapter 4. I didn't want to tack this onto that last video because it was already getting kind of long. So everything's up on D2L. I'm going to start doing chapter 5 videos, get them up as quickly as I can, so make sure you check back. Appreciate all the hard work. Hope these videos are helping. Grades are looking really good. So keep it up. Thanks a lot. See ya.